Our universe holds secrets that defy our most fundamental stories. The tale of a single explosive beginning is compelling, but it is also incomplete. What if the cosmos is far older, stranger, and more mysterious than the standard narrative allows? By the end of this journey, you will possess a radically different perspective on cosmic origins, built from 25 forgotten and astonishing facts. We will explore how the first second remains a complete mystery to physics, and why the universe might be shaped like a vast, repeating hall of mirrors. What is the one cosmic question you have always wanted answered? The very first second of cosmic history is a blank page in our physics textbooks, but what if the entire book has the wrong publication date? Our first forgotten fact challenges the most sacred number in cosmology. For decades, the age of the universe has been confidently stated as 13.8 billion years. This figure is derived from a beautiful, interlocking story. We measure how fast the universe is expanding today. We trace that expansion backwards in time, and we arrive at a moment of infinite density, the Big Bang. Yet this entire calculation rests on a single, critical assumption that the expansion rate has been constant and predictable. What if it has not been? A growing crisis known as the Hubble tension reveals a crack in this foundation. We have two primary ways to measure the universe's expansion. One method looks at the early universe at the faint afterglow of the Big Bang and calculates how fast space should be expanding now. The other method looks at nearby stars and galaxies, measuring their speeds directly. These two methods should give the same answer. They do not. They disagree by a significant margin. The newer, direct measurements from instruments like the James Webb Space Telescope suggest the universe is expanding faster than the early universe data predicts. This is not a small error in measurement. It is a fundamental discrepancy. One startling interpretation is that our universe is not 13.8 billion years old. If it has been expanding faster than we thought for all this time, then tracing its history backward would take longer. It could be billions of years older. This single possibility unravels threads we thought were tightly woven. It forces scientists to re-examine ideas long relegated to the fringe. Could the redshift of light from distant galaxies, the key evidence for expansion, be caused by something else? An old idea called the tired light hypothesis suggested light simply loses energy over vast cosmic distances, mimicking the effects of an expanding universe without the need for a Big Bang. While most evidence strongly disfavors this, the Hubble tension reminds us that our models are not perfect. We built a magnificent cathedral of cosmology on the bedrock of a constant expansion. Now that bedrock feels less solid, and in the shifting ground, forgotten questions are stirring once more. That single, sacred number is just the beginning of our story's unraveling. The very name we use for the origin of everything is itself a misdirection, a cosmic misnomer that has shaped our imagination for generations. Our second forgotten fact is this: there was no bang in the beginning. Forget every image you have ever seen of a brilliant, fiery explosion erupting into a dark, empty void. That is not what happened. The Big Bang was not an explosion of matter flying outward through pre-existing space. It was the rapid, unimaginable expansion of space itself. This is a distinction so profound it changes the entire picture. An explosion has a center and an edge, a shock wave racing into a surrounding medium. The Big Bang had neither. It happened everywhere at once because at that first moment, everywhere was the same single point. To understand this, think of a loaf of raisin bread dough before it goes into the oven. The raisins are scattered throughout the dough. Now, as the bread bakes, the entire loaf expands. Every single raisin moves away from every other raisin. From the perspective of any one raisin, all the others are receding, and no raisin is at the true center of the expansion. The dough itself is the fabric that is stretching. This is metric expansion, the stretching of the very fabric of space-time. carrying galaxies along with it like raisins in an ever-growing cosmic loaf. This idea was so radical and counterintuitive that many brilliant minds rejected it outright. The most famous critic was the astrophysicist Fred Hoyle. In a 1949 radio broadcast, while passionately arguing for an alternative theory called the steady-state model, which proposed a universe with no beginning, constantly creating new matter, he dismissively referred to the opposing idea as that Big Bang idea. He meant it as a mocking term, a label for what he saw as an unscientific and almost theological notion of a sudden creation. The name, intended as an insult, stuck. And in a beautiful twist of cosmic irony, the evidence Hoyle helped uncover would eventually bury his own steady-state model and solidify the very theory he named in jest. So when you hear Big Bang, do not think of a bomb. Think of the silent, instantaneous inflation of reality itself, a moment where the concepts of here and there, before and after, simply lost all meaning. This realization leads us to an even more unsettling question. If space itself can stretch, what other impossible properties might it hold? Space itself stretching from a single point is a concept that bends the mind, but it leads to a question that physics has long treated as forbidden. Our third forgotten fact confronts the ultimate taboo: what came before the Big Bang? For decades, the official scientific stance was that this question was meaningless. The Big Bang was the beginning of time itself, so asking what happened before time existed was like asking what is north of the North Pole. It was a logical error. Yet, this tidy dismissal always felt unsatisfactory, a philosophical dead end. A handful of theorists refused to accept it, and their sidelined ideas are now experiencing a dramatic resurgence. One of the most poetic is the cyclic model. Imagine the universe not as a single story with one dramatic opening chapter, but as an endless, breathing book. In this view, our universe expands from a Big Bang, evolves for trillions of years until stars burn out and black holes evaporate, leaving a cold, dark, and nearly empty expanse. Then, through processes we do not yet understand, this vast emptiness contracts not into a point, but into a supremely dense state that then triggers a new Big Bang. The cycle repeats forever. Our universe is just one heartbeat in an eternal cosmic rhythm, with no true beginning and no final end. A related idea is the bouncing universe. Here, our universe is not the first, but the latest in a series. A previous universe contracted in a big crunch, but instead of collapsing to an infinitely small point, it reached a maximum density where quantum physics took over, causing it to bounce back outward in our Big Bang. In this scenario, time does exist before our beginning. It is simply the timeline of a prior cosmos. Perhaps the most mind-expanding concept comes from the realm of quantum gravity and string theory. It suggests that what we call the Big Bang was not a unique event but a local phenomenon. Picture a boundless, churning ocean of primordial energy, a quantum foam. Within this frothing sea, bubbles of space-time can spontaneously inflate. Our entire universe is one such bubble, one stable region that inflated spectacularly from a quantum fluctuation in a much larger, possibly eternal, meta-universe. In this multiverse model, Big Bangs are happening all the time elsewhere. Our cosmic home is not special, it is just one island in an infinite archipelago of realities, each with its own laws of physics. These ideas were long dismissed as untestable metaphysics, but modern cosmology is bringing them in from the cold. The precise patterns in the cosmic microwave background, the afterglow of our bang, could potentially hold faint imprints or scars from a previous cosmic cycle or a collision with another bubble universe. We are now looking for the fingerprints of eternity in the oldest light we can see. The question of what came before is no longer meaningless. It is the next great frontier, and the answers may reveal that our universe is far from alone. The possibility of a cosmos before our own shatters the simple story of a single beginning, but it also exposes a profound silence at the very heart of our origin tale. Our fourth forgotten fact stares into that silence. The first second of the universe is not just unknown, it is fundamentally unknowable to our current laws of physics. This period, split into epochs with names like the Planck Epoch and the Grand Unification Epoch, is a complete blank in our cosmic history book. To understand why, we must shrink our perspective to an almost impossible scale. Picture the universe a mere 10 to the minus 43 seconds old. At this instant, the entire cosmos was smaller than a single subatomic particle. In this realm, the familiar rules of Einstein's gravity and the quantum world of particles cease to function. They clash, producing nonsensical answers like infinite density and infinite temperature. It is the equivalent of a calculator displaying error when you try to divide by zero. Our physics simply breaks down. During this unfathomably brief moment, something miraculous is theorized to have occurred. All four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single, supreme force. There was no distinction between the glue that holds atoms together and the curvature of space-time itself. They were one and the same. This state of perfect symmetry is what physicists call the Grand Unification Epoch. Then, in a fraction of a second, as the universe expanded and cooled, this perfect symmetry shattered. One by one, the forces froze out, separating from each other like water crystallizing into different forms of ice. This breaking of symmetry is what gave our universe its structure, but we have no equations to describe the moment it happened. This is why the hunt for a theory of everything is not merely an academic exercise, it is a quest to recover our own lost genesis. The leading candidates, like superstring theory and loop quantum gravity, are attempts to write the rules for that first second. Superstring theory proposes that the fundamental ingredients of reality are not point-like particles, but incredibly tiny, vibrating loops of energy. The different vibrations of these strings would produce all the particles and forces we see, potentially describing that unified state. Loop quantum gravity takes a different path, suggesting that spacetime itself is not smooth and continuous, but woven from a fabric of tiny, discrete loops. At the scale of the early universe, this granularity of space and time would prevent the infinities that break our current models, allowing us to peer back before the Big Bang into a possible previous cosmic phase. These ideas remain unproven, mathematical symphonies waiting for an experimental note. They represent humanity's most ambitious attempt to answer a simple, haunting question: what were the rules of reality when there was almost no reality at all? The first second is the ultimate locked door, and behind it may lie the reason everything else exists. The locked door of the first second conceals a mystery even our best theories cannot yet open, but the story of our universe's infancy does not end there. A monumental idea now dominates our textbooks, an addendum to the Big Bang so powerful it feels inseparable from the original theory. This is cosmic inflation, the notion that a fraction of a second after the beginning, the universe underwent a period of hyper-fast, exponential expansion, smoothing it out and planting the seeds for galaxies. Yet this was not the only idea on the table. Our fifth forgotten fact resurrects a brilliant, discarded rival, the quasi-steady-state model. In the 1990s, even as inflation was cementing its victory, the legendary astronomer Fred Hoyle, alongside Geoffrey Burbidge and Jayant Narlikar, proposed a radically different vision. They could not accept a single, definitive beginning. Instead, they envisioned an eternal universe, one with no start and no end, but not a static one. In their model, the cosmos expands overall, but within it, new matter is continuously created. This creation does not happen uniformly. It occurs in violent, localized events they called mini-bangs or creation fields. Picture a calm, infinite ocean. Every so often, from the depths, a colossal bubble of new energy and matter violently erupts, pushing the existing water outward and creating a new region of cosmic material. These mini-bangs would explain the expansion we see, the existence of galaxies, and even the cosmic microwave background radiation, which they argued was not a fading echo of one Big Bang, but the accumulated starlight from an infinite past, recycled and thermalized over eons. For a time, this was a legitimate competitor. It elegantly solved certain puzzles, like why the universe appears so uniform on large scales, without needing a magical episode of inflation. It preserved a kind of eternal, self-renewing cosmos that many found philosophically satisfying. So why did it lose? The evidence slowly and decisively turned against it. The quasi-steady-state model predicted specific patterns in the cosmic microwave background that simply did not match the exquisite, detailed maps produced by satellites like COBE and WMAP. The distribution of galaxies on the largest scales also failed to align with its predictions. Most damningly, it could not naturally explain the precise proportions of the lightest elements, hydrogen and helium, forged in the first few minutes, which the standard Big Bang model predicts with stunning accuracy. Inflation, for all its own unresolved questions, simply matched the data better. The quasi-steady-state model faded into the footnotes, a beautiful and ambitious idea that the universe itself seemed to reject. Yet its existence is a crucial reminder. Our current scientific orthodoxy was not inevitable. It emerged from a fierce battle of ideas, and the losers in that battle often contained sparks of genius that still illuminate the darkness at the edge of our understanding. The desire for an eternal cosmos did not die with that model. It merely transformed, seeking new outlets in the multiverse and cyclic theories we have already glimpsed. The fading echoes of cosmic battles leave us with a universe ready to take shape, but the question of what that shape was made from remains. Among the most persistent shadows in cosmology is the mystery of dark matter, an invisible substance that outweighs all visible stars and galaxies 5-1. One of the most elegant and largely forgotten solutions to this puzzle emerged from the universe's first chaotic moments. This is the story of primordial black holes. Forget the colossal black holes that lurk in galactic centers, born from dying stars. Primordial black holes are something else entirely. They are theorized to have formed not from stellar collapse, but from the raw pressure of the universe's birth. In the first second, when space was a seething, dense soup, tiny regions of slightly higher density could have been squeezed by the overwhelming pressure into microscopic knots of gravity. These knots would have become black holes, some as small as an atom, others as massive as a planet. For a time, this idea was a leading candidate to explain dark matter. The logic was beautifully simple. These ancient black holes would be dark, they would not interact with light, and they would have the gravitational heft to explain how galaxies hold themselves together. They could be hiding everywhere in vast numbers, their collective gravity shaping the cosmos from the shadows. Yet the story takes a strange and famous turn thanks to Stephen Hawking. He discovered that black holes are not completely black. Due to quantum effects at their very edge, they slowly leak radiation and lose mass, a process now called Hawking radiation. For a stellar black hole, this evaporation is imperceptibly slow, taking longer than the current age of the universe. But for a tiny primordial black hole, the story is different. The smaller a black hole is, the faster it evaporates. A black hole with the mass of a small asteroid would have evaporated in a brilliant flash of radiation by now. This prediction created a tantalizing possibility. The final moments of a primordial black hole's evaporation would be a violent gamma-ray burst of energy. For decades, astronomers have scanned the skies for these telltale flashes, the last screams of these ancient cosmic fossils. They have not found them. The absence of these flashes has severely constrained the idea, pushing most primordial black holes out of the running as the primary component of dark matter. They could still exist in certain mass ranges, lurking unseen, but they are no longer the favored solution. This elegant hypothesis, born from the turbulence of the Big Bang and refined by one of the greatest minds of our time, now sits in a curious limbo, not quite proven, not quite discarded. It is a ghost in the machine of cosmology, a reminder that some of the universe's first children might have lived, died, and left only a silence we are still straining to hear. The silence of those first cosmic children leaves us with a universe that, by all rights, should not exist at all. This is not philosophical speculation, but a cold, hard prediction from our most trusted physics. Our seventh forgotten fact confronts the most profound asymmetry in all of existence, the mystery of why there is something rather than nothing. Specifically, why is the universe made almost entirely of matter? The laws of physics, as we understand them, are beautifully symmetrical. For every particle of matter created in the Big Bang, an identical particle of antimatter should have been created as its mirror twin. Antimatter is not science fiction, it is real. It has the same mass as normal matter, but the opposite electric charge. When a particle meets its antiparticle, they annihilate each other in a flash of pure energy. According to the textbook story, the hot, dense early universe should have been a perfect factory, producing matter and antimatter in absolutely equal amounts. Then, as the cosmos cooled, every particle should have found its antiparticle, and they should have mutually destroyed each other, leaving behind a vast, empty, and lifeless expanse of light. Yet here we are, in a universe filled with galaxies, stars, planets, and us. This means that for every billion pairs of matter and antimatter particles that annihilated in the first second, one single particle of matter was left over. 1 in a billion survived. That tiny, fragile surplus is everything we see. Everything you are made of is the residue of that 1 in a billion imbalance. So what caused it? The quest to answer this is called baryogenesis, and it requires a violation of nature's perfect symmetry. In the 1960s, the Soviet physicist Andrei Sakharov outlined 3 conditions that must be met for matter to win out. First, the universe must be out of thermal equilibrium, meaning it cannot be a perfectly smooth, uniform soup. It needs some kind of disturbance or phase transition, like water suddenly freezing into ice. Second, there must be processes that do not conserve baryon number. Baryons are particles like protons and neutrons, the building blocks of atoms. The old rule was that the total number of baryons in the universe must stay constant. Sakharov said this rule had to be broken, allowing the universe to create a net surplus of matter over antimatter. Third, and most subtle, there must be a violation of both charge conjugation and parity symmetry, known together as CP violation. This is a deeply technical concept, but its meaning is simple. It means the laws of physics must treat matter and antimatter slightly differently, and they must also distinguish between right-handed and left-handed particles. The universe must have a tiny, built-in bias. We have actually observed CP violation in delicate experiments with subatomic particles like kaons and B mesons. The effect is real, but it is frustratingly small. The amount of asymmetry we have measured in our particle accelerators is far, far too weak to account for the overwhelming dominance of matter in our cosmos. It is like finding a single bent coin and trying to explain an entire mountain of gold. So the mystery deepens. The Sakharov conditions give us a recipe, but we are missing the most potent ingredients. Somewhere in the extreme energies of the universe's first moments, a process occurred that favored matter on a colossal scale. This could have happened during the grand unification epoch, when forces were one, or perhaps during the inflationary expansion itself. This critical imbalance is often glossed over in popular tales of the Big Bang, treated as a minor footnote, but it is not a footnote. It is the single most important event after creation itself, the reason there is a cosmos to observe at all. Without it, reality would be a silent, featureless flash. The search for the source of this asymmetry is now a driving force in particle physics, because in that forgotten flicker of bias lies the reason for our entire material existence. That delicate imbalance between matter and antimatter set the stage for everything to come, but the universe was still a featureless, searing fog. To find the blueprint for our cosmic home, we must listen to its oldest song. Our eighth forgotten fact is that the cosmic microwave background is far more than a fading afterglow. It is a frozen snapshot of the infant universe, and its hidden patterns hold secrets we are only beginning to decipher. Picture the universe 380,000 years after the Big Bang. Before this moment, it was an opaque plasma, a thick soup of particles and light where photons could not travel freely. Then, as it expanded and cooled, electrons and protons combined to form neutral hydrogen atoms. The universe suddenly became transparent. The light that was finally set free from that fog has been traveling for over 13 billion years, stretched and cooled by the expansion of space into the faint microwave glow we detect today. This is the CMB, and its most shocking feature is not that it exists, but how perfectly uniform it is. No matter where you point a radio telescope in the sky, the temperature of this background radiation is almost exactly the same, to within 1 part in 100,000. This presents a profound puzzle called the horizon problem. 2 points on opposite sides of the sky are so far apart that light has not had enough time since the Big Bang to travel between them. They have never been in contact, never exchanged heat or information. How then did they reach the same temperature? It is as if 2 people in separate, soundproof rooms who have never met or spoken began humming the same note at the same pitch with perfect synchronization. This impossible uniformity was one of the strongest clues that led to the theory of cosmic inflation. That brief, hyper-fast expansion in the universe's first fraction of a second would have stretched a tiny, homogeneous region to encompass our entire visible cosmos, explaining why it all looks the same. But buried within that near-perfect uniformity are the most important imperfections in the cosmos. Those tiny anisotropies, fluctuations in temperature of mere millionths of a degree, are not noise. They are a cosmic treasure map. These faint hot and cold spots are imprints of the quantum fluctuations that were present in the universe during inflation. Microscopic ripples in the fabric of spacetime were stretched to astronomical sizes, becoming the seeds for all future structure. The slightly denser regions, shown as slightly cooler spots in the CMB, had a little extra gravity. Over billions of years, they pulled in more matter, eventually growing into the vast cosmic web of galaxies and galaxy clusters we see today. By meticulously mapping these patterns with satellites like Planck, cosmologists can read this ancient text. The specific statistical distribution of the hot and cold spots tells us the precise geometry of the universe, confirming it is flat to an extraordinary degree. The patterns also reveal the amount and nature of dark matter and dark energy, acting as a cosmic accounting ledger. The acoustic peaks in the map, like frozen sound waves in the early plasma, tell us the composition of the universe down to the decimal point. So this faint, cold glow is not just a relic. It is the universe's first photograph, its birth certificate, and its architectural plan, all rolled into one. We are literally reading the wrinkles on the face of creation to understand what it was destined to become. That ancient photograph of light reveals the universe at 380,000 years old, but a far older messenger left the scene much earlier. Long before the cosmic microwave background was set free, the universe was already broadcasting a different, ghostly signal. This is the cosmic neutrino background, and it is the oldest fossil in all of creation. To understand its story, we must go back to just 1 second after the Big Bang. At that moment, the cosmos was still a seething, dense plasma, completely opaque to light. Photons were trapped, constantly bouncing off a thick soup of electrons and protons. But for another type of particle, the universe was already an open book. These are neutrinos, the most ghostly and abundant particles with mass in the universe. Trillions of them pass through your body every second, interacting with almost nothing. This same property made them the first particles to escape the primordial fog. About 1 second after the beginning, as the universe expanded and cooled, neutrinos stopped interacting with the rest of the cosmic soup. They decoupled, flying freely through space, never to be significantly disturbed again. This means that while the light in the CMB shows us the universe at 380,000 years old, the cosmic neutrino background is a snapshot from its first second of life. It is a relic over 300,000 times older. This sea of ancient neutrinos is still everywhere, permeating all of space. You are swimming in it right now. Yet detecting it is a challenge of almost unimaginable difficulty. These neutrinos have been traveling for over 13 billion years, and the expansion of the universe has stretched their wavelengths and sapped their energy. They are now incredibly cold, moving at speeds only slightly slower than light. To catch one of these ghosts, we would need a detector of impossible scale, perhaps a tank of ultra-pure water or heavy liquid the size of a planet. So why do we care about a signal we can barely hope to measure? Because this forgotten background holds secrets that no other probe can reveal. First, it could tell us the exact masses of neutrinos. We know these particles have some mass, but we do not know how much, and this unknown factor influences how structures like galaxies and galaxy clusters formed. The gravitational pull of that primordial sea of neutrinos would have subtly shaped the cosmic web we see today. Second, and more profoundly, these neutrinos are direct witnesses to the universe's very first second. They carry unaltered information from an epoch before nucleosynthesis, before even most protons and neutrons were stable. If we could ever decipher their faint signal, we might learn details about the grand unification of forces or the conditions that led to the matter-antimatter asymmetry. They are silent travelers from a time before time had any real meaning, holding in their faint vibrations the forgotten first chapter of everything. The silent neutrino sea was a witness to the universe's first second, but the next 3 minutes wrote the first chapter of its elemental story. This was the era of Big Bang nucleosynthesis, the forge where the lightest atoms were hammered into existence. In a frantic burst of nuclear fusion, protons and neutrons collided to form the cores of hydrogen, helium, and a tiny trace of lithium. The calculations for this process are a triumph of modern cosmology, predicting the cosmic abundances of hydrogen and helium with breathtaking precision. Yet there is a glaring, persistent error in this otherwise perfect equation. It is known as the cosmological lithium problem, and it represents a crack in our understanding of the universe's first moments. The models tell us exactly how much lithium-7, the most common stable isotope of that element, should have been created in that primordial furnace. When we then look at the oldest stars in our galaxy, relics from near the dawn of time whose atmospheres should preserve that original chemical mix, we find a discrepancy. These ancient stars contain only about 1/3 of the predicted lithium. It is not a small measurement error. It is a factor of 3, a major mismatch that has stubbornly resisted explanation for decades. Where did all the lithium go? One forgotten possibility involves the ghostly particles we just discussed, neutrinos. What if they played a more destructive role than we thought? Some exotic models suggest that if neutrinos are slightly more interactive or have certain unexpected properties, they could have disrupted the delicate nuclear reactions in that first 3 minutes, essentially burning up lithium as fast as it was made. Another intriguing, though highly speculative, solution points to the decay of hypothetical particles from the grand unification epoch. Imagine heavy, exotic particles predicted by theories beyond the standard model, relics from the universe's first fraction of a second. As these particles decayed, they could have injected extra neutrons or photons into the primordial soup, subtly altering the nuclear chain reaction and reducing the final lithium yield. A more conventional, but no less fascinating, forgotten path looks at the nuclear physics itself. Our calculations rely on laboratory measurements of how certain atomic nuclei interact. What if, in the extreme, searing conditions of the early universe, some of these nuclear reaction rates were different? A slight change in the probability of a key step, like the fusion of helium-3 and helium-4 to form beryllium-7, which then decays into lithium-7, could resolve the entire problem. It is a reminder that we are applying physics measured in earthly labs to an environment of unimaginable temperature and density, a place we can never recreate. The lithium problem is often overshadowed by the grand mysteries of dark matter and dark energy, but its persistence is a profound clue. It suggests that something is missing from our picture of the universe's first few minutes, a forgotten ingredient or a slight misreading of the nuclear recipe. Solving it would not just fix a number in a textbook, it would give us a clearer, more accurate window into the moment the very first atoms were born. The missing lithium whispers of an incomplete recipe, a sign that our first few minutes are not yet fully understood. Yet the greatest ingredient of all, the one that holds galaxies together, remains not just mysterious in its nature, but in its very birth. We know dark matter exists by its gravitational hand, but we have forgotten to ask a more fundamental question: when and how was dark matter created? The standard assumption is that it is a relic, a particle that froze out of the searing heat of the Big Bang, much like the cosmic neutrino background. For decades, the prime candidate has been the WIMP, the weakly interacting massive particle. These hypothetical heavy particles would have been produced in great numbers in the early universe, then annihilated with each other until their density dropped so low that they could no longer find each other to destroy, leaving behind a stable remnant that forms the dark matter we infer today. It is an elegant story, but after decades of searching in underground labs and particle colliders, we have found precisely nothing. The silence is deafening, forcing cosmologists to revisit forgotten and exotic alternatives born in the universe's first instance. One of the most compelling is the action. This hypothetical particle was not invented to explain dark matter at all. It was proposed to solve a deep and unrelated puzzle in quantum physics called the strong CP problem, which asks why the strong nuclear force seems to perfectly respect certain symmetries. The action is a light, ghostly particle that would naturally emerge as a solution. In the chaotic conditions of the early universe, these actions could have been produced in colossal numbers, not through particle collisions, but through a mechanism akin to a cosmic field settling into its lowest energy state, like a marble finally coming to rest at the bottom of a bowl. As this field oscillated, it would have released a coherent sea of actions, a wave of dark matter washing over the cosmos. Because they are so light, actions would behave more like a pervasive, quantum fluid than discrete particles, potentially explaining the smooth distribution of dark matter in galactic cores. Another ghost from the first second is the sterile neutrino. Ordinary neutrinos are left-handed, meaning their spin is oriented opposite to their direction of motion. A sterile neutrino would have no such handedness and would interact only through gravity, making it truly dark. These could have been produced not in the hot plasma, but through oscillations in the primordial neutrino sea, a kind of quantum identity swap in the universe's first second. The production mechanism is critical because it dictates how dark matter clumps together. Did it emerge hot, moving at near light speed and smoothing out small structures, or cold, moving slowly and allowing galaxies to form early? The debate is not just academic. The precise pattern of the earliest, tiniest galaxies we are now finding with the James Webb Space Telescope could be the long-awaited clue, a fossil imprint of dark matter's forgotten moment of birth. The identity of this shadow substance is more than a missing puzzle piece. It is a direct message from a time before atoms, and we are only just learning how to listen. Dark matter's birth is a shadowy mystery, but its counterpart presents an even deeper cosmic riddle. The energy of empty space is not zero. This is our 12th forgotten fact, a truth so bizarre it redefines nothingness. We call its effect dark energy, the mysterious force accelerating the expansion of the universe, but its origin is an ancient ghost in the equations of physics. The story begins not in the late 1990s with the discovery of the accelerating cosmos, but in 1917 with Albert Einstein himself. He had just applied his new theory of gravity, general relativity, to the entire universe. To his dismay, the equations insisted the universe must be either expanding or contracting. This clashed with the prevailing belief in a static, eternal cosmos. To force his model into alignment with this belief, Einstein introduced a fudge factor, a term he called the cosmological constant. It represented a repulsive energy inherent to the fabric of space itself, a kind of anti-gravity that could precisely balance the inward pull of all matter, holding the universe in a steady state. A decade later, when Edwin Hubble proved the universe was indeed expanding, Einstein famously called the cosmological constant his greatest blunder, and the idea was discarded for generations. The universe, it seemed, did not need a vacuum energy, yet the ghost refused to die. In the late 1990s, two independent teams of astronomers were measuring the distances to far-off supernova, using them as cosmic mile markers to see how the expansion rate had changed over time. Everyone expected to find that gravity was slowing the expansion down. The shock was absolute. The data revealed the expansion was not slowing at all, it was speeding up. Some mysterious repulsive force acting against gravity on the largest scales was pushing galaxies apart faster and faster. The long-forgotten cosmological constant was resurrected overnight. The energy of the vacuum, empty space itself, was real. But this triumphant rediscovery immediately led to the most embarrassing problem in all of theoretical physics. When we try to calculate how much energy empty space should have using our best theory of the small quantum mechanics, we get a number, and it is catastrophically, unimaginably wrong. Quantum theory suggests that even in a perfect vacuum at the tiniest scales, particles and fields are constantly flickering in and out of existence. This quantum foam should be seething with energy. Summing up all these microscopic fluctuations should give the vacuum an enormous density, a tremendous repulsive power. The calculated value is about 10 to the power of 120 times larger than the tiny value we actually observe from the acceleration of the cosmos. That is a 1 followed by 120 zeros. It is the worst mismatch between prediction and observation in the history of science. To say the vacuum energy is fine-tuned is a cosmic understatement. If it were just a little bit larger, even by a minuscule fraction, the repulsive force would have been so powerful in the early universe that it would have ripped apart every proton, neutron, and atom before they could ever form. No stars, no galaxies, no life. If it were zero, gravity would have long ago pulled the cosmos back into a big crunch. Our existence depends on this number being almost, but not exactly, zero to an absurdly precise degree. This is the cosmological constant problem. It suggests we are missing something fundamental, a principle that cancels out almost all of this vacuum energy, leaving behind only the faintest whisper we now call dark energy. Some theorists propose a forgotten symmetry in nature, or perhaps an as yet unknown connection between the quantum world and gravity. Others wonder if the answer lies in the multiverse, where every possible value of the cosmological constant exists in some bubble universe, and we simply find ourselves in one of the rare habitable ones where the number is almost zero. The energy of nothing may be the ultimate clue that our understanding of reality is still profoundly incomplete. Dark energy's faint whisper shapes the expansion of space, but the fabric it stretches may hold a secret geometry. We have measured the universe and declared it flat, but flatness describes local geometry, not global shape. A forgotten question lingers, one that could rewrite our map of reality entirely. What is the universe's true topology? Is it simply infinite and flat, like an endless sheet of paper? or could it be finite but unbounded, folding back on itself in a hidden pattern? This is not science fiction. Consider the surface of the Earth. It is finite, yet you can walk forever in a straight line without ever reaching an edge. It is a two-dimensional sphere. Now try to imagine a three-dimensional equivalent. One compelling possibility is a 3 torus. Picture a cube where, if you walk out of the right wall, you instantly re-enter from the left wall. If you fly out of the top, you return from the bottom. This creates a finite, closed universe with no boundaries, a cosmic hall of mirrors on the grandest scale. In such a cosmos, the light from a single galaxy could, given enough time, travel all the way around the universe and appear to us as a duplicate, a ghost image in the opposite sky. An even more elegant shape is the Poincaré dodecahedral space. Here, the universe is imagined as a vast, curving dodecahedron, a 12-sided shape where each face is connected to its opposite with a twist. This intricate topology would wrap the cosmos into a beautifully ordered, finite package. The profound implication of any finite shape is that the universe is not immeasurably vast but contained. It would have a size we could, in principle, calculate. So how do we search for the walls of this cosmic room? We look for the repeating patterns they would impose on the oldest light we have, the cosmic microwave background. In an infinite, simply connected universe, the hot and cold spots in that afterglow are all unique. But in a finite, wrapped universe like a 3 torus, the patterns would repeat. Light would have taken multiple paths to reach us, tracing giant circles in the sky where the temperature fluctuations match perfectly. Astronomers have scoured the CMB maps from the Planck satellite for these matched circles, the ghostly fingerprints of a wrapped cosmos. So far, they have found none. The search has come up empty, suggesting that if our universe is finite, it must be larger than the distance light has had time to travel since the Big Bang, hiding the repeating seams from our view. Yet the possibility remains tantalizingly open. A finite universe would answer a deep philosophical question. It would mean all of existence is, in some profound sense, here. We would not be looking out into an endless, unknowable void, but rather inhabiting a cosmic island with a knowable structure. The silence of the data has pushed this line of inquiry to the speculative fringe, but it refuses to die. It reminds us that knowing the universe is flat is only the first step. Understanding its shape, whether it is a boundless plane or an elegantly folded origami of space-time, is a forgotten frontier that still waits for its detective. The universe's shape, whether infinite or folded, is a canvas waiting for its first masterpiece of light. That masterpiece required a single, transformative event, a moment so profound it is often reduced to a footnote in the cosmic story. 380,000 years after the beginning, the universe finally became transparent. This is the epoch of recombination, and its physics are far more delicate than a simple snap of the fingers. For nearly 400 millennia, the cosmos was an opaque, searing fog. Free electrons, negatively charged, swarmed everywhere. Photons, the particles of light, could not travel more than a tiny distance without crashing into one of these electrons, scattering wildly in a process called Thomson scattering. Light was trapped, a prisoner in a plasma, but the universe was relentlessly expanding and cooling. As the temperature dropped, the average energy of particles diminished. Eventually, it became low enough that positively charged protons could capture these free electrons, binding them into orbits to form the first atoms of neutral hydrogen. This was recombination, the marriage of protons and electrons. Crucially, this was not an instantaneous, universe-wide event. It was a process that unfolded over tens of thousands of years, a gradual fading of the fog. As more and more electrons were captured, the paths for photons grew clearer. The last scattering surface is not a sharp wall in time, but a diffuse shell around us, a final fog bank from which the oldest light in the universe finally escaped. The moment a photon made its last scatter and began its unimpeded journey is the moment captured in the cosmic microwave background we detect today. That light is a fossil of the universe's last moment of opacity. But with this brilliant liberation came a profound cosmic silence. The era of light had ended and the Dark Ages began. With all the free electrons now bound into atoms, the universe became electrically neutral and transparent. There were no stars, no galaxies, only vast, drifting clouds of dark matter and neutral hydrogen gas. For the next several 100 million years, the cosmos was a truly dark and simple place. The only light was the steadily redshifting afterglow of recombination, fading from visible glow to microwave whisper. This quiet epoch was the necessary prelude to everything. Within those immense dark clouds, gravity worked slowly, patiently pulling the denser regions of dark matter and gas together. The Dark Ages were not an empty void, but a nursery of potential, a cosmic incubation period where the seeds revealed in the CMB finally began to grow in earnest, setting the stage for the first stars to violently end the long night. That profound cosmic silence was the necessary prelude to creation. For nearly 200 million years, the universe existed in a state of pure potential, a featureless expanse known as the Dark Ages. This period is not merely an empty gap in our timeline, it is a forgotten epoch where the most important gravitational work was done in utter darkness. With a brilliant afterglow of recombination fading into a cold microwave whisper, the cosmos was left with only two ingredients: vast neutral clouds of primordial hydrogen and helium gas, and the invisible scaffolding of dark matter. There were no light sources, no landmarks, just an ocean of simple atoms drifting through an expanding void. Yet within this perfect darkness, the faint blueprints imprinted during inflation began to stir. Those microscopic quantum ripples, now stretched to cosmic scales, meant some regions of the universe were ever so slightly denser than others. The extra dark matter in these regions exerted a stronger gravitational pull. Slowly, imperceptibly over millions of years, this invisible skeleton began to draw the neutral gas toward it. Picture a mountain range slowly rising from a flat plain, its peaks gathering mist and cloud. The dark matter formed these cosmic mountains, and the hydrogen gas was the mist flowing into their gravitational valleys, creating the first protogalactic halos. Within these halos, something extraordinary began to happen. As the gas pooled and condensed, it started to heat up through friction and collisions. Eventually, in the densest cores of these structures, the pressure and temperature crossed a critical threshold. The first nuclear furnace ignited. These were not stars like our Sun. They were the universe's first stellar generation, known as population 3 stars. They were monsters, behemoths that could be hundreds of times more massive than our own star. Composed purely of the primordial elements, hydrogen and helium, they burned with a ferocious, ultraviolet intensity. Their formation was a violent end to the Dark Ages, a blaze of light tearing through the cosmic fog. But their life was tragically short. Such massive stars consumed their nuclear fuel in only a few million years before dying in spectacular supernova explosions. These cataclysmic deaths were just as important as their births, for they forged and scattered the first heavy elements like carbon, oxygen, and iron into the surrounding gas. This stellar pollution seeded the cosmos with the raw materials for rocky planets, complex chemistry, and eventually life itself. The Dark Ages were not an empty intermission. They were the quiet, determined gathering of forces before the universe's first great act of illumination, an act that would forever change the chemical destiny of everything to come. The violent birth of those first stars did more than just pollute the cosmos. It sent a shockwave through the very fabric of space. This event, poetically called the Cosmic Dawn, has left behind a ghostly radio signature that we are only now learning how to hear. It is a whisper on a very specific frequency, 21 centimeters, and it comes from the most abundant element in the universe, neutral hydrogen. To understand this forgotten echo, we need to revisit the end of the Dark Ages. The vast seas of hydrogen gas were cold and quiet. Each hydrogen atom is a simple system, a single proton orbited by a single electron. These two particles act like tiny magnets, and they can spin in two possible configurations, aligned or opposite. The opposite spin state has a very slightly higher energy. If an electron flips from the high energy state to the low energy state, the atom releases the extra energy as a photon with a wavelength of exactly 21 centimeters, a faint radio wave. In the cold, dark universe, these flips were rare, but then the first stars ignited. Their intense ultraviolet radiation did something extraordinary. It excited the surrounding hydrogen gas, making the electron spin flips more common and causing the gas to absorb some of the background radiation from the cosmic microwave background. Later, as those first stars died and their X-ray radiation heated the gas, the signal would change again, emitting a 21-centimeter glow. This means the neutral hydrogen acted as a giant cosmic radio transmitter, broadcasting the entire story of the cosmic dawn, the timing, the location, and the intensity of the first stellar births and deaths. By tuning our radio telescopes to the right frequency, redshifted by the expansion of the universe, we could in principle map the structure of the infant cosmos in 3 dimensions, watching the first galaxies flicker on like lights across a dark continent. The hunt for this signal is one of cosmology's greatest technical challenges. It requires isolating an incredibly faint whisper from a cacophony of earthly radio interference and brighter galactic radio sources. Leading this frontier is an experiment called EDGES, the experiment to detect the global epoch of reionization signature. In 2018, the EDGES team announced something astonishing. They may have detected the absorption signal from the cosmic dawn. But the signal was far stronger and deeper than any standard model predicted. It suggested the primordial hydrogen gas was much colder than anyone thought possible, or that the background radiation from the CMB was much hotter at that time. Either scenario points to physics beyond our current understanding. Perhaps interactions with dark matter cooled the gas, a direct fingerprint of that shadow substance at work. Or maybe there was an unexpected source of radio waves bathing the early universe. The finding remains controversial, not yet confirmed by other experiments, but it has electrified the field. It is a reminder that the universe's first light may hold secrets we have not even begun to imagine, and that listening to its oldest radio station could rewrite the story of our cosmic dawn. That ghostly radio whisper from the cosmic dawn hints at forces we have barely begun to map. Among the most subtle and overlooked architects of cosmic structure are magnetic fields. We tend to think of magnetism as a local phenomenon, the force that guides a compass or holds a note on a refrigerator. Yet magnetism may be a cosmic birthright woven into the fabric of the universe from its earliest moments. The idea of primordial magnetic fields is a quiet but persistent thread in cosmology. These would not be the strong, organized fields we see in galaxies today, but faint, chaotic seeds generated in the turbulent plasma of the infant cosmos. One theory suggests they were created during the phase transitions of the early universe, when the fundamental forces separated from their unified state. Picture the universe cooling like water turning to ice. As it underwent this cosmic freezing, immense energies were released, creating violent turbulence in the seething primordial soup. This churning of charged particles could have stretched and twisted weak electromagnetic fields, amplifying them into a vast diffuse network. Another possibility points to the inflationary epoch itself. Quantum fluctuations during that hyper-fast expansion could have generated not just density variations, but also tiny electromagnetic ripples stretched to cosmic scales. So why does this matter for a universe ruled by gravity? Because these weak primordial fields could have played a surprisingly important role as cosmic sculptors. As the first clouds of gas collapsed under gravity to form stars and galaxies, even a faint magnetic field would have exerted a force. It could have provided a source of friction, slowing the collapse in some regions and guiding the flow of gas along invisible lines of force. This subtle guidance might have influenced the spin of the first galaxies and helped channel material into the disks we commonly observe. Perhaps more dramatically, these ancient fields are prime suspects in explaining one of astrophysics' great mysteries, the origin of ultra-high-energy cosmic rays. These are subatomic particles, often protons, that strike our atmosphere with energies millions of times greater than anything produced in our most powerful particle colliders. Their source is unknown. A widespread, weak magnetic field permeating the universe could act as a vast accelerator and a labyrinth. It could confine these particles, whipping them around for millions of years, boosting their energies to staggering levels before they finally escape and streak across the cosmos. The field would also scramble their paths, making it impossible to trace them back to a single source like a distant quasar or galaxy, which is exactly the problem astronomers face. The evidence for these primordial fields remains elusive but not absent. Some studies of the cosmic microwave background have searched for subtle twists in its polarization, a signature that could be imprinted by such fields. Others look at the alignment of light from distant galaxies, which could be rotated as it passes through a magnetized intergalactic medium. So far, the results are inconclusive, placing only limits on how strong such a field could be. Yet the possibility endures, a reminder that the empty spaces between galaxies are not truly empty. They may be threaded with the faint, fossilized magnetism of creation itself, a forgotten force that quietly helped mold the universe we see today. Magnetism's cosmic origins lead to a strange and specific prediction, one so problematic it helped force a revolution in cosmology. Grand unified theories, those ambitious frameworks seeking to merge the fundamental forces, come with a peculiar consequence. They predict the existence of magnetic monopoles. Unlike every magnet you have ever seen, which always has both a north and a south pole, a monopole is a hypothetical particle that carries just one, a solitary north or a solitary south. It would be a fundamental magnetic charge as basic as an electric charge. In the searing heat of the grand unification epoch, when forces were one, the physics suggests these exotic particles should have been produced in staggering abundance. They would be incredibly massive, perhaps as heavy as a bacterium compressed into a single point, and nearly indestructible. According to straightforward calculations, the early universe should have created so many monopoles that they would dominate the mass budget of the cosmos today. We should be tripping over them. Their collective gravity would have overwhelmed everything else, and the universe would look nothing like it does. Yet, despite decades of sensitive searches, from deep underground labs to cosmic ray detectors, not a single confirmed magnetic monopole has ever been found. They are utterly absent. This glaring mismatch between a beautiful theory and an empty reality is known as the monopole problem, and for a time it threatened to derail the entire enterprise of grand unification. The solution, of course, was cosmic inflation. That brief period of hyper-fast expansion did more than just smooth out the universe. It acted as the ultimate cosmic dilutant. Think of a single drop of ink in a tiny thimble of water. The ink is concentrated, dark, and obvious. Now, imagine instantly expanding that thimble into an ocean. The same drop of ink is now spread so thin it becomes completely undetectable. Inflation did exactly this to magnetic monopoles. The prodigious number created in that first fraction of a second was suddenly diluted across a volume of space so immense that their density plummeted to nearly zero. In our entire observable universe, there might only be a handful, making their detection a matter of incredible luck rather than expectation. This is why the monopole problem is largely forgotten today. It was a crisis so neatly solved by inflation that it now stands as one of that theory's earliest and strongest pieces of indirect evidence. The absence of something became a powerful clue. We do not see monopoles precisely because inflation happened, erasing their signature from our cosmic neighborhood and allowing the universe we recognize to take shape. It is a profound reminder that sometimes the most important evidence is not what we find, but what we do not. The absence of magnetic monopoles is a silent testament to inflation's power, but that same inflationary epoch may have unfolded in a space far stranger than we perceive. Our 19th forgotten fact ventures into the most mathematically elegant and physically elusive of all origin stories, one where the universe began with more than 3 dimensions. String theory, the leading candidate for a theory of everything, does not just suggest extra dimensions, it requires them. For the complex equations of strings to produce the particles and forces we see, the universe must have 9 or 10 dimensions of space, not the 3 we experience. Where are the others? The theory proposes they are compactified, curled up into shapes so incredibly tiny, perhaps at the Planck scale, that they are completely hidden from our perception. To understand this, picture a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink yourself to the size of an ant and crawl onto its surface, you would discover it has a second dimension, a circular dimension wrapped tightly around its length. Our reality could be analogous, with 6 or 7 extra spatial dimensions curled into complex, microscopic shapes at every single point in space. This is not just a mathematical curiosity. If these dimensions exist, their specific geometry, the way they are folded and knotted at the quantum level, determines the very laws of physics in our 3-dimensional realm. The size of these curled-up dimensions would set the values of fundamental constants, like the strength of gravity or the mass of an electron. A slight change in their configuration would produce a universe with entirely different physics, one where atoms might not be stable or forces too weak to form stars. Now apply this to the universe's origins. In the first unimaginable moments, all dimensions, including the extra ones, may have been on an equal footing, all unfurled and large. As the universe cooled and underwent its phase transitions, perhaps only 3 of those dimensions were selected by the dynamics of inflation to expand spectacularly, while the others collapsed and stabilized into their tiny, hidden forms. This process of dimensional stabilization could have been a violent, chaotic event, imprinting itself on the fabric of space-time. Some speculative models suggest that the energy released as these extra dimensions compactified could have even fueled the inflationary expansion itself, or created unique signatures in the gravitational wave background of the universe, a fossil vibration we might one day detect. It is a breathtakingly speculative idea, a forgotten facet of origin theories that pushes the boundaries of imagination. While we lack any direct experimental proof for these hidden dimensions, their potential influence is profound. They remind us that the stage upon which our cosmic drama plays out may be far more intricate than it appears, and that the deepest rules of reality could be written in the geometry of spaces too small to see. Hidden dimensions and curled-up geometries speak to a universe with rules written in a language we cannot yet read, but there is a deeper silence at the very beginning that challenges our understanding of reality itself. The Big Bang singularity is not just a point of infinite density, it is a wall of oblivion. This 20th forgotten fact confronts the information paradox of creation, a philosophical shadow that makes the origin of everything profoundly unknowable. In physics, information is not just data, it is a sacred principle. It refers to the complete set of properties that describe every particle in a system, its position, its momentum, its spin. The laws of quantum mechanics suggest this information is never truly lost. It may be scrambled or hidden, but it is conserved. This principle faces its greatest test in black holes, where matter and light vanish behind an event horizon, seemingly erased from the universe. This is the famous black hole information paradox. Yet the singularity at the start of our universe presents an even more absolute version of this problem. The Big Bang is not an event horizon we can approach. It is a temporal boundary, a first moment before which we cannot see. All the equations of general relativity break down there, rendering the concepts of before and after meaningless. Any information about what preceded that moment, if such a concept even applies, was not just hidden behind a curtain. It was incinerated in the furnace of the singularity itself. The universe, in a very real sense, began with a cosmic amnesia. This has staggering implications for causality, the chain of cause and effect that structures our reality. If no information can survive from before the Big Bang, then our cosmos is fundamentally a causal. It has no traceable cause in the classical sense. Everything we see, from the largest galaxy to the smallest atom, emerges from a state of total informational reset. Some physicists, like Stephen Hawking, suggested this means we must abandon the idea of a singular beginning altogether, replacing it with a no-boundary proposal where time becomes like another dimension of space, smoothing out the singularity into a finite but unbounded geometry, like the North Pole on a globe. In this view, asking what happened before the Big Bang is like asking what is north of the North Pole. The question dissolves. Others, drawing from quantum gravity, speculate that information might not be lost but transformed or encoded in the very structure of the expanding spacetime, perhaps in the pattern of the cosmic microwave background or the quantum state of the universe itself. Yet the haunting possibility remains that some truths about existence are permanently locked away, that the universe genuinely sprang from nothing in the most complete sense, with no prior blueprint, no inherited memory, and no answer to the ultimate question of why there is something rather than nothing. The silence of the singularity is the loudest unanswered question in cosmology, reminding us that our story may have no first chapter, only a title page that reads, "Let there be light." That cosmic amnesia at the singularity leaves us with a universe whose basic rules seem inexplicably perfect. This perfection is not a matter of beauty, but of breathtakingly precise numbers. The strength of gravity, the mass of an electron, the energy in empty space, these fundamental constants appear to be dialed to values that allow for atoms, stars, planets, and life. If any one of them were altered by even a fraction of a percent, the universe would be sterile, a void without structure or light. This observation leads to our 21st forgotten fact, a philosophical firestorm known as the anthropic principle. In its simplest form, it states that the universe must be compatible with the existence of observers because we are here to observe it. This sounds almost trivial, but its implications have divided scientists for decades, pushing a profound debate into the shadows. On one side are those who see this fine-tuning as the ultimate clue, not about our universe but about what lies beyond it. Their explanation is the multiverse. If there are an infinite number of universes, each with randomly different physical constants, then of course we find ourselves in one of the rare life-permitting bubbles. In this view, there is no deeper reason for the tuning. It is simply a cosmic lottery, and we hold the winning ticket. The anthropic principle becomes a selection effect, a statistical necessity. This idea was often dismissed as a cop-out, an untestable retreat from the scientific quest for a single, elegant explanation. Yet, with the rise of inflationary cosmology and string theory, which naturally suggest a landscape of possible universes, the multiverse interpretation has gained a startling amount of traction. It reframes the question from why are the constants so perfect to what physical process generates the diversity of universes in which we could arise. The opposing camp finds this deeply unsatisfying. They argue that accepting the anthropic principle as an answer is to abandon the core mission of physics, which is to find a fundamental, causal theory that predicts these constants from first principles. They seek a single, beautiful equation, a theory of everything that leaves no dials to be tuned, where the constants are the only possible values locked in by the logic of mathematics. For them, the fine-tuning is not a bizarre coincidence, but a signpost pointing toward a deeper layer of reality we have not yet uncovered. The controversy lies in the tension between these two visions of science. Is our universe a unique masterpiece with a discoverable reason for its laws, or is it one page in a near-infinite book of random possibilities? This forgotten debate is not merely academic, it shapes where we look for answers. If you believe in a single explanatory theory, you pour energy into unifying relativity and quantum mechanics. If you lean toward the multiverse, you search for its fingerprints in the cosmic microwave background or in the detailed structure of the laws themselves. The anthropic principle forces a humbling admission that our existence might be an irreducible part of the cosmic story, and that sometimes the most important fact about the universe is the one asking the questions. The philosophical debate over fine-tuning forces us to confront a profound alternative, a vision of the cosmos that once promised eternal stability. The steady-state theory was not merely a scientific mistake, it was a beautiful and influential dream that shaped the course of modern cosmology. Its core premise was both simple and deeply appealing. The universe has always existed and will always exist with no singular beginning and no ultimate end. To maintain this eternal, unchanging appearance in the face of observed expansion, the theory proposed a radical idea: the continuous creation of matter. New hydrogen atoms would spontaneously appear in the vast empty spaces between receding galaxies, just enough to keep the overall density of the cosmos constant over time. This was a universe without a birth certificate, a cosmos in perfect equilibrium, forever renewing itself. The aesthetic and philosophical elegance of this model captivated many brilliant minds, including Fred Hoyle, who co-proposed it. It removed the need for a mysterious initial event, a singularity that defied physics. It presented a cosmos that was infinite in both space and time, a comforting and grand vision. Yet the steady state was far more than a philosophical alternative. It was a powerful competitor that forced the Big Bang model to prove itself. Hoyle and his colleagues did not sit idly by. They actively sought evidence to support their view and to challenge their rivals. In doing so, they made predictions that would become central to cosmology, though not in the way they expected. One of the most significant involved the temperature of the universe. The steady-state model predicted that the universe should be filled with the accumulated starlight from an infinite past, recycled and thermalized into a faint, uniform glow. This was a necessary consequence of an eternal cosmos. When Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background in 1965, it was initially seen as a potential victory for the steady state. Here was the predicted universal radiation, but the critical detail was the temperature. The CMB was far too cold, a mere 2.7 degrees above absolute zero. This temperature perfectly matched the prediction from Big Bang nucleosynthesis, the cooling of a hot, dense early universe. It was the precise thermal fingerprint of a fiery beginning, not the lukewarm bath of ancient starlight. This was the decisive blow. The steady-state theory had correctly predicted the existence of a background radiation, but its properties belonged irrevocably to the Big Bang. The irony is profound. The theory's own quest for evidence helped seal its demise and validate its greatest rival. The legacy of the steady state is therefore not one of simple error. It is a legacy of rigorous competition. By demanding testable predictions and forcing cosmologists to sharpen their arguments, it accelerated the discovery of the CMB and helped establish the rigorous, evidence-based standard that defines modern cosmology. Its ghost lingers in our continued unease with a singular beginning, pushing us to ask if our universe is part of a larger, perhaps eternal, multiverse. The dream of an endless cosmos may have faded, but its challenge forever changed how we search for our origins. The dream of an eternal cosmos was beautiful, but the evidence pointed to a fiery beginning. Yet even that beginning required a blueprint, a pattern from which everything could grow. The source of that pattern is one of the most profound miracles in all of science. Every galaxy, every star, every planet you see, including the one beneath your feet, can trace its origin back to a subatomic tremor, a quantum hiccup in the nothingness that preceded time. This is the story of quantum fluctuations as cosmic seeds, a fact so often repeated that its staggering elegance can be forgotten. To grasp it, we must shrink our perspective to the smallest possible scale, to the universe a fraction of a second after its birth during the inflationary epoch. In this realm, the concept of empty space loses all meaning. According to quantum mechanics, a perfect vacuum is not still. It is a seething, bubbling foam where pairs of virtual particles and antiparticles constantly wink in and out of existence, borrowing energy from the void for an instant before annihilating each other. This is the quantum noise of reality itself. During inflation, the universe was dominated by a strange energy field, the inflaton field. Like the quantum vacuum, this field was not perfectly smooth. It was subject to tiny, random fluctuations, microscopic ripples in its energy level. These ripples were quantum uncertainties made real, as unpredictable as the exact moment a single radioactive atom will decay. Then inflation performed its magic. That period of hyper-fast expansion did not just make the universe large, it took those infinitesimal subatomic ripples and stretched them to astronomical sizes. A quantum wobble smaller than a proton one moment could, in the next unimaginably brief instant, be inflated to a scale of light years. Imagine taking the faintest whisper of static from an untuned radio and with the pull of a cosmic lever, amplifying it into the full, complex symphony of a galactic orchestra. That is what inflation did. These stretched fluctuations became permanent imprints in the density of the universe. Regions where the inflaton field was slightly higher in energy became slightly denser as that extra energy converted into a tiny excess of particles after inflation ended. Regions where it was slightly lower became underdense. This created a faint cosmic fingerprint of hot and cold spots in the primordial plasma. Gravity then took over. Those slightly denser patches had a tiny bit more gravitational pull. Over hundreds of millions of years, they acted as seeds, drawing in more and more dark matter and gas from their surroundings. The underdense regions emptied out, becoming the vast cosmic voids we see today. The gravitational collapse of those overdense seeds is what eventually formed the first stars, the first galaxies, and the great cosmic web that spans the observable universe. The profound implication is that the largest structures in existence are direct descendants of the smallest events possible. The majestic spiral of the Andromeda Galaxy and the delicate orbit of the Earth around the Sun are, in their deepest origin, the amplified echoes of quantum jitters. This connection between the quantum world and the cosmic scale is perhaps the most important discovery in modern cosmology. It means the universe did not begin with a preordained plan for grandeur. It began with a microscopic chaos, a quantum dice roll, whose results were then frozen into the fabric of space-time and grown by gravity into the breathtaking cosmos we call home. Our entire reality is built on a foundation of random, microscopic noise, sculpted by immutable physical laws into an ordered, beautiful, and living universe. That quantum dice roll created the seeds, but it left behind a glaring cosmic contradiction. How could the universe be so perfectly uniform if its pieces had never spoken to each other? This is the horizon problem, a paradox that once threatened to unravel the entire Big Bang story. Consider 2 points on opposite sides of the cosmic microwave background. They are separated by over 90 billion light years, a staggering distance. Yet the temperature of the radiation coming from both points is identical to within a few millionths of a degree. According to the Standard Model, light has only had 13.8 billion years to travel. These two regions are so far apart that light from one could never, even in the entire age of the universe, have reached the other. They have been causally disconnected since the beginning, like two people in soundproof rooms on opposite sides of the world who have never met. How could they possibly have coordinated to reach the exact same temperature? It would be like two orchestras playing in separate, isolated halls with no conductor and no communication, beginning a symphony at precisely the same moment, with every musician hitting the exact same note. This impossibility haunted cosmology for years, a fundamental flaw in an otherwise successful theory. The solution arrived not with a bang, but with a whisper of mathematical elegance from physicist Alan Guth in 1980. His idea was cosmic inflation, a brief but spectacular event in the universe's first fraction of a second. Before inflation, the observable universe was an unimaginably tiny speck, far smaller than a single proton. This entire region was causally connected, meaning light signals could zip across it instantly, allowing it to reach a perfectly uniform temperature, a state of thermal equilibrium. Then inflation struck, driven by a strange repulsive energy inherent to empty space itself. This subatomic speck underwent a period of exponential, hyper-fast expansion. In less than a trillionth of a second, it ballooned by a factor of at least 10 to the 26. That tiny, homogeneous, connected region was stretched to a size larger than our entire observable cosmos today. The horizon problem simply vanished. The entire sky we see was once a single, tiny neighborhood where every particle knew every other particle. Inflation took that local uniformity and stretched it across the heavens, explaining why everything looks the same in all directions. But Guth's flash of insight did more than solve one puzzle. It solved several at once with breathtaking economy. It explained the remarkable flatness of the universe, why space appears to obey the rules of Euclidean geometry on the largest scales. A tiny, curved region inflated to such an immense size would appear flat to any observer inside it, just as a small patch of the Earth's surface feels flat to someone standing on it. Most beautifully, it provided the origin story for those quantum fluctuations. The microscopic ripples in the inflattened field were stretched to cosmic proportions, becoming the density variations that seeded all future galaxies. Inflation was a triple triumph, a single, elegant mechanism that answered the horizon problem, the flatness problem, and provided the seeds for structure, all in one conceptual swoop. It transformed cosmology from a collection of puzzling observations into a coherent, predictive narrative. Yet for all its power, this elegant fix remains a theory in search of its final, definitive proof, a whisper from the first moment that we are still straining to hear. Inflation's elegant solution gave us a universe, but it left its ultimate destiny an open question. Our final forgotten fact looks beyond the expansion we see today, to the often ignored menu of cosmic endings that await. The most commonly discussed fate is the Big Freeze or heat death. In this scenario, dark energy continues to accelerate the expansion forever. Galaxies recede beyond each other's cosmic horizons, their light fading from view. Stars burn out, black holes slowly evaporate via Hawking radiation, and over trillions upon trillions of years, the universe becomes a cold, dark, and nearly empty void. All usable energy is spent, and the cosmos reaches a state of maximum entropy, a uniform, lifeless sea of photons and elementary particles drifting infinitely far apart. It is a quiet, lonely, and seemingly inevitable conclusion, but it is not the only one. A more violent destiny is the Big Rip. This hinges on a specific, phantom form of dark energy that grows stronger over time. If this is the true nature of the force accelerating our expansion, its repulsive power would eventually overcome every binding force in the universe. First, galaxy clusters would be torn apart, then individual galaxies. As the end approaches, stars would be ripped from their orbits, planets from their stars. In the final moments, atoms themselves would be shredded, their nuclei torn apart, and finally, the very fabric of space-time would be ruptured. the universe would end not with a whimper, but with a catastrophic, fundamental disintegration of reality. A third and more cyclical possibility is the Big Crunch. This is the classic rebound ending where the expansion eventually slows, halts, and reverses. All matter and energy would come rushing back together in a mirror image of the Big Bang, culminating in a singularity of infinite density. This scenario, once popular, fell out of favor with the discovery of dark energy's acceleration. Yet it remains plausible if dark energy is not constant, but a dynamic field that could decay or reverse in the far future. A crunch could trigger a new Big Bang, leading to the cyclic universe models we explored earlier, an endless cosmic heartbeat. The most exotic and unsettling ending is vacuum decay. This arises from the idea that our universe exists in a false vacuum state. Think of our current laws of physics as a stable valley, but not the lowest possible valley in the cosmic landscape. A quantum tunneling event, perhaps triggered by a high-energy particle collision in a distant galaxy, could create a tiny bubble of true vacuum. This bubble would expand at the speed of light, its walls rewriting the fundamental constants of physics as they go. Atoms, forces, and the very nature of reality would cease to exist within it, replaced by something entirely different and likely inhospitable to any structure we know. The change would be permanent and unstoppable, erasing our universe without warning. So which of these forgotten fates is ours? The clues are hidden in the detailed behavior of dark energy. Is its strength constant, or is it changing? Is it phantom energy or something else? The answer will be written in the fate of the most distant galaxies we can observe, and in the subtle stretching of the cosmic web over billions of years. The ultimate destiny of everything, from the largest galaxy to the smallest thought, hangs on the nature of that mysterious, silent force that even now is pulling the cosmos apart. 25 forgotten threads woven together reveal a tapestry far richer than the simple story of a single explosive beginning. Our journey has taken us from the unknowable first second, where physics itself breaks down, to the ghostly echoes of ancient neutrinos and the silent shaping of dark matter. We have seen how the universe might be far older than we thought, how its very shape could be a folded hall of mirrors, and how its most fundamental forces were born from the shattering of a perfect symmetry. The lithium problem whispers of a misread nuclear recipe, while the hunt for primordial magnetic fields suggests invisible architects at work. From the cosmic dawn's faint radio song to the terrifying possibility of vacuum decay, each fact peels back a layer of our cosmic origin story, exposing not a tidy narrative but an ongoing, breathtaking mystery. This is the true legacy of our exploration, not a list of answers, but a deeper, more profound set of questions. It reminds us that science at its best is not a monument of settled facts, but a living, breathing conversation with the unknown. We are the universe becoming conscious of itself, piecing together its own forgotten history from faint whispers in the dark. So, which of these 25 facts reshaped your understanding of reality the most? Was it the quantum dice roll that seeded every galaxy, or the staggering fine-tuning that allows us to be here to ask these questions? Let the conversation continue. Share your mind-blowing moment in the comments below. If you crave more journeys to the edge of understanding, subscribe and join us as we keep unraveling the deepest mysteries of space, time, and existence. The cosmos has forgotten more than we will ever know, but the quest to remember it defines who we are.